Hello.
Hi. Did you know there's a logic for the complexity class NP? This is great because if you want to teach your math students NP, you don't have to introduce Turing machines.
Oh, that's interesting. What is this logic?
It's called ESO for existential second-order logic. And the result is due to Fagin. An existential second-order sentence is a formula of the following form. We may existentially quantify our relations R1 up to Rk. Then comes a usual first-order formula, whose signature also contains the existentially quantified relations. So the NP-complete 3 colorability problem for graphs may be expressed in ESO via a sentence which quantifies over 3 unary relations that stand for red, green, and blue, and which states that each vertex must be red, green, or blue, and that if 2 vertices are adjacent in the graph, then not both ends of the edge can have the same color. Fagin's theorem states that an isomorphism closed class of finite structures is in NP if and only if it can be expressed in ESO.
I prefer deterministic polynomial time computation. Is there such a nice logic for P?
If your input structure is ordered, then yes, it's called fixed point logic. I will illustrate fixed point logic with an example by showing how to use it to express that a given digraph is acyclic, that is, has no directed cycles. I work with inflationary fixed point logic, which is one of the many fixed point logics of equal expressive power. Inflationary fixed point logic is an extension of first-order logic by so-called inflationary fixed point constructors. The idea for expressing acyclicity is that we may define a transitive closure of the edge relation of the digraph. A transitive closure contains E and is transitively closed, which we can write down as a first-order formula. The inflationary fixed point constructor applied to this formula returns the smallest relation that contains E and is transitively closed. So the sentence that states that this relation does not contain loops holds on a given digraph if and only if the digraph is acyclic. Every fixed point sentence can be evaluated on finite structures in polynomial time. If the input is restricted to ordered structures, then fixed point logic captures precisely the complexity class P.
And without the ordering?
Unfortunately, in this case, fixed point logic cannot even express the property whether a given finite structure has an even number of elements. This is called the parity problem.
So isn't there an extension of fixed point logic that would be able to express the parity problem?
Yes, there is. It's called FPC for fixed point plus counting. Unfortunately, FPC cannot express the satisfiability of systems of linear equations.
So what about extending fixed point logic with some linear algebra primitives?
This has also been studied. It's called FP plus rank.
And is FP plus rank a candidate for a logic for P?
This is actually a famous open research problem. To the best of my knowledge, this is even open for the class of finite domain constraint satisfaction problems. Constraint satisfaction problems are computational problems that can be specified elegantly by fixing a structure B with a finite relational signature, for example, a directed graph. The domain of B might be finite or infinite. The input consists of a finite structure A that has the same signature as B. And the computational task is to decide whether A maps homomorphically to B. The 3 colorability problem that we have already seen earlier is the constraint satisfaction problem for the 3-element clique. An important constraint satisfaction problem over the domain 0,1 has 2 ternary relations that express linear equations with 3 variables, modulo 2. This problem is essentially the satisfiability problem for systems of linear equations over the 2-element field. The graph acyclicity problem is an example of a constraint satisfaction problem that can only be formulated if we allow the domain of the structure B to be infinite.
Which finite domain CSPs are in P?
This question has been solved in 2017 independently by Bulatov and by Jakub, confirming the famous Fedor-Vardy dichotomy conjecture. The polynomial time tractable cases have a quite elegant universal algebraic characterization. A finite domain CSP is in P if and only if all the constraints are preserved by a so-called weak near-unanimity operation. A weak near-unanimity operation is an operation of arity at least 2 that satisfies the following identity. If x and y are elements of the domain B, and all arguments of the operation are equal to x except for at most one exception y, then the operation returns the same value independently from where the exceptional argument appears. The binary minimum operation, that returns the smaller of its arguments, is an example of such an operation. Operations that preserve all relations of a structure B are called polymorphisms of B.
So what is known about the expressibility of finite domain CSPs in fixed point logic without the rank operator?
If a finite domain CSP is expressible in fixed point plus counting, it is even expressible in data log, which is the existential positive fragment of fixed point logic. Finite domain CSPs in data log are described by the following theorem, which follows from combining results of Atzerias, Bulatov and Davar, Barto and Kojic, and Marotti and Mackenzie. The constraint satisfaction problem for a finite structure B is in data log, if and only if it is in fixed point logic with counting, if and only if B has weak near unanimity polymorphisms of almost all arities, if and only if B cannot simulate systems of linear equations by so-called primitive positive constructions, or short PP constructions, which are a very powerful tool for obtaining reductions between CSPs. It follows from results of Atzerias, Bulatov and Davar that PP constructions preserve expressibility in fixed point logic.
For which classes of infinite domain CSPs can we expect a similar characterization of expressibility in data log and in fixed point logic?
There's a very large class of infinite structures, namely reducts of finitely bounded homogeneous structures, where a dichotomy P versus NP complete has been conjectured. This would properly generalize the dichotomy of Bulatov and Juk for finite structures.
And are there some classes of infinite domain CSPs where such a dichotomy has already been proved?
Yes, this is for example known for the fundamental class of so-called temporal CSPs. Temporal CSPs are constraint satisfaction problems where all constraints are quantifier-free formulas over some infinite linear order. I usually use the order of the rationals for this order because it is homogeneous and has quantifier elimination. So acyclicity is an example of a temporal CSP, but also the so-called betweenness problem. There the constraints are ternary. A solution to a set of betweenness constraints is a linear order such that for each constraint the middle argument must appear in the middle with respect to this linear order. This is an NP-hard problem, just as the cyclic ordering problem. There are also many interesting temporal CSPs in P. For example, the and/or scheduling problem, where the constraints are again ternary, and which say that x must appear before the minimum of y and z in the linear order that we are looking for. This problem can be solved in linear time. Oort-Horn constraints have been studied in the temporal reasoning community in artificial intelligence and can also be solved in polynomial time. The computational complexity of temporal CSPs has been completely classified by Jan Kara and myself. There are precisely 9 different polynomial time tractable classes. All other temporal CSPs are NP-complete.
What do the tractable classes look like?
Again, they are given in terms of certain polymorphisms. 2 of the polymorphisms are easy to describe. The operation min, which returns the minimum of its 2 arguments, and its dual, the operation max. If all the constraints of a temporal CSP are preserved by min, then the CSP can be solved in polynomial time. The other polymorphisms are more tricky to describe. However, in each of the polynomial time tractable cases, there is a weak near unanimity polymorphism modulo endomorphisms. An operation of arity 2 is called a weak near unanimity operation modulo endomorphisms if there are endomorphisms of B, that is homomorphism from B to B, such that the weak near unanimity identity that we have seen earlier holds after applying the endomorphisms E1 up to EK to the terms of the identity. In fact, a temporal constraint satisfaction problem is in P if and only if the temporal structure B for the CSP has weak near unanimity polymorphisms modulo endomorphisms, unless P equals NP, of course.
So how about the expressibility of temporal CSPs in fixed point logic? Do we also have a collapse of data log and fixed point logic?
No. Actually, already the and/or precedence constraints problem that I mentioned earlier cannot be expressed in data log. This is an old result of Jan Kara and myself from 2010, But it's easy to express this problem in fixed point logic. And/or precedence constraints can be solved as follows. If we have an instance of this problem, we first look for variables that can become the minimum in a solution. Clearly, if a variable x participates in a constraint that says that x must be larger than the minimum of y and z, then x is not a candidate for such a variable. The set of all other variables, however, can be made the minimum in some solution. So we remove this set and all incidence constraints and continue recursively. It is quite clear that this procedure can be formulated with fixed point logic. However, as I already said, and/or constraints cannot be solved in Datalog.
So which temporal CSPs are expressible in fixed point logic?
Actually, I don't know.
And which temporal CSPs are expressible in Datalog?
I also don't know.
But do you at least have some concrete examples of temporal CSPs where you don't know whether they are expressible in fixed point logic or in Datalog?
Yes, there's one temporal CSP, which is in P, where I strongly suspect that it's not in Datalog, and probably not even in fixed point logic.
Okay.
It has an extremely interesting CSP, with one ternary relation which I call X. The relation capital X is the relation that consists of all triples where two entries are equal and one is bigger. There is a connection between instances of the constraint satisfaction problem for X and an interesting linear algebra problem. Note that the relation X contains in particular the tuple 0, 0, 1, 0, 1, 0, and 1, 0, 0. We translate an instance of the CSP by translating each constraint on x, y, z into the Boolean linear equation, which says that x plus y plus z is equivalent to 0 modulo 2. Now, the original CSP has a solution if and only if the resulting system of linear equations has a non-trivial solution for all subsets of the constraints. By a non-trivial solution, I mean a solution which maps at least one of the variables that appears in the constraints to 0 and at least one of the variables that appears in the constraints to 1.
You mentioned a conjecture that would generalize the theorem of Pulatov and Juk to the reducts of finitely bounded homogeneous structures. Do you also have a conjecture that would generalize the Datalog dichotomy of Barto, Kožík, Acerias, Bulatov and Dawar?
I was wondering whether maybe the existence of weak near-unanimity polymorphisms of almost all arities modulo endomorphisms could be a condition for expressibility in fixed point logic. And whether perhaps the PP constructibility of linear equation systems might be the only reason for not being expressible in fixed point logic. But I really don't know. These are just questions.
So many questions. I have to think about them. Ahoy, Manuel.
Hey, how are you? What have you been doing all these years?
I think I have an answer to your question. I now know precisely which temporal CSPs are expressible in fixed point logic.
Really? So which temporal CSPs are in fixed point logic?
So I can show that all of the polynomial time tractable cases can be expressed in FP, except for one case which contains the relation x. On the other hand, I can show that the CSP for the relation x cannot even be expressed in fixed point logic with counting. Finally, I can show that all temporal CSPs which cannot PP construct the relation x and which cannot PP construct all finite structures are contained among the cases for which I can show expressibility in FP. This gives us a complete classification.
Great. So how do you show containment in fixed point logic?
So I proceed in two steps. In the first step, I reduce the task to expressibility for specific temporal CSPs, and in the second step, I provide such FP sentences. I will illustrate this on an example of temporal CSPs which are preserved by the operation min. Temporal CSPs that are preserved by min can be described as follows. A relation R over Q is preserved by min and all endomorphisms of Q if and only if R has a primitive positive definition over the strict order and a version of the and/or precedent constraints with weak inequalities. Since expressibility in fixed point logic is preserved by primitive positive definability, it therefore suffices to present a fixed point formula for CSPs with constraints formed using these two relations only. It is not difficult to translate the polynomial time algorithm for temporal CSPs preserved by the operation min to fixed point logic. This solves the CSP that we have just seen. The other algorithms from your paper with Jan Kara can unfortunately not be translated directly to fixed point logic. However, I have found some non-trivial modifications that allows for formulations in FP.
Interesting. So how do you prove that the remaining temporal CSPs cannot be expressed in fixed point logic?
Again, my proof has two parts. All temporal CSPs that are not in P can PP construct all finite structures. And it follows from the results mentioned earlier that they are not in FPC. On the other hand, if a temporal CSP is in P, then I can prove that it can either PP construct your particular relation X, or that it falls in one of the cases where I have a fixed point algorithm. So it suffices to prove that the CSP for the relation X cannot be expressed in fixed point logic. Here I use an old construction of Shelah and Gurevich, so-called multipedes. Here is an illustration of a multipede. In order to show that a particular class of structures is not in FP, one usually constructs pairs of structures such that one of the structures is in the class and the other is not, and such that the structures cannot be distinguished using first-order formulas with a bounded number of variables. The isomorphism problem for multipedes can be used to produce systems of homogeneous linear equations that have no non-trivial solution over the two-element field, but this fact cannot be inferred from viewing at a bounded number of variables. This construction can be adapted to produce a satisfiable and an unsatisfiable instance of the CSP for our relation X that cannot be distinguished in first-order logic with a bounded number of variables.
Do you also know which temporal CSPs are in data log?
Yes, I do. I can prove a very strong negative result. The expressibility of temporal CSPs in data log cannot be described by any term identities for polymorphisms.
Oh, too bad. And how about my question about expressibility in fixed point logic? Does PP constructability of linear equation systems characterize non-expressibility in fixed point logic for temporal CSPs?
It does not. I can show that the relation X cannot PP construct linear equation systems over any non-trivial abelian finite group.
And how about my question about weak near-unanimity polymorphisms of almost all arities modulo endomorphisms? Do they characterize temporal CSPs in fixed point logic?
No, this is again not true. The relation X has weak near-unanimity polymorphisms of arity 3 and all larger arities modulo endomorphisms, but its CSP is not in FP.
So is there any algebraic characterization of the temporal CSPs in fixed point logic?
Yes, there is. A temporal CSP can be expressed in fixed point logic if and only if there are polymorphisms satisfying the following system of height 1 identities, which I call E34. The system involves 4 operations of arity 3. Know that if all of these 4 operations would be equal, then the system is equivalent to the weak near-unanimity condition. To gain some intuition why this system is relevant, we verify that the relation X does not have such polymorphisms. If a temporal relation contains the tuples 1, 0, 0, 0, 1, 0, and 0, 0, 1, which is the case for X, and we apply one of the operations gi to these tuples, we must obtain a tuple which is again in X. So exactly 2 of the resulting entries must be minimal. The satisfiability of E34 implies the existence of a 4-tuple resulting from the 4 lines of the identities on the left, whose projections onto any 3 entries are also contained in the relation. This means that for each of the 4 subsets of 3 entries of the 4-tuple, exactly 2 among them are minimal, which is clearly impossible. On the other hand, I can show that temporal relations which cannot PP construct X or all finite structures do have polymorphisms witnessing the identities E34.
So could this condition be a characterization of expressibility of fixed point logic for the larger class of reducts of finitely bounded homogeneous structures?
No, because there are examples in this class due to Cherlin, Shelach and Shi, which show that the expressibility of the CSPs from this class in fixed point logic cannot be characterized by any finite set of height 1 identities for polymorphisms. But the condition E3,4 can be generalized to conditions E, K, K plus 1, and it could be the case that a CSP from this class is expressible in fixed point logic if and only if its polymorphisms satisfy EK, K plus 1 for all but finitely many arities.
And can you prove this for the class of finite domain CSPs?
Yes, I can. On the one hand, finite domain CSPs which are expressible in fixed point logic have weak near-unanimity polymorphisms for all but finitely many arities, and these imply the conditions EK, K plus 1. And on the other hand, I can show that the condition EK, K plus 1 can be satisfied by affine combinations over the cyclic group Zn if and only if K and N are coprime. And this rules out those finite domain CSPs which are inexpressible in FP.
Because those can't have EK, K plus 1 for all but finitely many K.
Yes.
I see. What do you think? Does least fixed point logic plus the rank operator express all polynomial times CSPs in the class of reducts of finitely bounded homogeneous structures?
I don't know.
There's another beautiful logic which is a candidate for a logic for P. It's choiceless polynomial time. What do you think? Our relation X, can the CSP for our relation X be expressed in choiceless polynomial time?
That I also don't know.
And I guess the same is open for choiceless polynomial time plus counting.
Yeah, I guess so.
This is an interesting open problem.